Today we have with us Vanguard. Bimal Mehta from Vanguard will be speaking about what are the different initiatives in quantum they are leading at one of the largest financial institutes in the world, and what are the different projects there in the finance and quantum computing domain for all of you to participate in. So I'll quickly introduce Bimal, and then the stage is all yours. So Bimal is the head of AI and machine learning engineering within the Center of Analytics and Insights in Vanguard. His primary role is to lead AI and ML pipelines for Vanguard's personal investor business. He's also part of Vanguard's enterprise quantum group that is responsible for exploring and advocating quantum computing use cases and applications in Vanguard. They started quantum computing only 3 years back, but since then they have already published a couple of papers. They are doing some amazing work. And today we have Bimal with us here to share all those exciting stuff with all of you. So over to you, Bimal. The stage is all yours.
Thanks, Vardaan. We primarily work in the field of AI and machine learning. I have almost 18 years of experience in that field. And I have my team also that has joined today. They are also part of this program that will also be assisting throughout this course with the project that we have come up with. It's Kyle Mahdi, who is also on the call, Disha Mehta, Raj Kanan, and Paras. So these are the four people who will be assisting throughout this course. And if you have any questions related to the project, right, they will be happy to help you. They'll be setting up all the logistics and everything. Now, quickly, before we jump into what we are doing, just giving an overview about Vanguard, what Vanguard is exactly, for people who are not aware about it, Vanguard. Vanguard is one of the largest asset management company today across the globe. It's headquartered in US in Pennsylvania in a city called as Melbourne. It started by John Bogle and has been there since the day it got incepted. So today, Vanguard basically manages roughly around $10.1 trillion in terms of assets under management. And that is the second largest after BlackRock. So people who are from the finance industry, like have heard about BlackRock. So they are number two after BlackRock. And today, most of the focus of Vanguard is around ETFs. So if you look over here, ETF basically is almost 33% of Vanguard's asset under management. And mutual funds contribute to the rest of the 6.8 trillion that you see over there. Last year in 2024, the global cash flow for Vanguard was 128.4 billion. This is as of April 2025. We have roughly 20,000 employees globally that are spread across multiple locations, and I'll show where we are spread across today. And we have today 50 million plus investors that have opened accounts with Vanguard, either through their institution or either through retail, either through personal investment. And today there are like 444 funds that Vanguard manages actively and passively across the US and across the globe. And if you look over here, it is one of the lowest expense ratio in the industry today. Like when you are trying to purchase a fund, Vanguard offers one of the lowest expense ratio. And down you will see where we have offices today. Primarily, our offices are headquartered, as I said, if you see the red dot, that's the global headquarters, which is Melbourne, located near to Philadelphia, started in 1975. But if you see, we are increasing our global presence, right? I'm based out of the Charlotte office, which started in 1997, and I'm based out of there. And today we have offices across Europe and Australia too. And the latest update is we opened our office just this year in India, in Hyderabad, and that will be operational from next year. So that dot that you see missing in India, that is not there, but that is one of the largest office that we are opening, and that will be ready from 2026. So that's about Vanguard, what we are doing, and what Vanguard is about. So let me quickly jump to the details about the project that we are thinking of having throughout this course and where we need participation from you guys. So I'll quickly share that one and walk you through what exactly we intend to do with that. So the project that we have selected for this particular series, that is where you will be actively participating for a few weeks and helping build it, related to portfolio optimization. That is one of the typical problems that you see in the financial services industry. And this problem that we have defined here is not the typical portfolio optimization kind of toy problem. This is an actual problem that we have set down last year. We investigated what needs to be done and exactly what we want to achieve out of this problem. So in this problem, we also did a limited experiment with IBM to prove out the value. Even our internal team that I introduced you, they have done their own experiments too. So we do have some benchmarks against which we can compare whatever you guys come up with. We do have benchmarks against which we'll be comparing that to see like, okay, which is a better solution. Now, why did we select this portfolio construction as the prototyping use case for this particular phase? The primary reason is that if you look at Vanguard's investment philosophy, it sits on four pillars: the goals, the balance, the cost, and the discipline. Now the goals basically is something you cannot really control. Those are more qualitative goals. But one thing is, when you set a goal, you have certain returns in mind. Let's say I want to get 10% return. I want to get 12% returns. I want to get 14% return. How do I basically construct my portfolio so I can achieve that particular goal? Second is, how do I balance it? Because today, if you look at it, we ourselves have 441 funds, Vanguard itself. But if I want to distribute my money across this 441 funds, how do I distribute? What is the optimum strategy to distributing that? It's not an easy problem to solve, because let's say if you have to distribute your money across 20 funds out of that 441, it takes a lot of computing power to determine that, because it has to go through every scenario, comparing every fund with every other fund, creating the correlation matrices, everything, and doing that. That's just about funds. What if I want to do the same allocation for underlying stock within that fund? That increases the compute power. So as the portfolio grows and as the mixture grows, this problem becomes like goes into the zone of NP hard. Like, it's very difficult to solve it on a classical computer. And today we have created certain models, like which is known as the VCAM, which is the Vanguard Asset Allocation Model, and the Vanguard Capital Market Model. Those are the two underlying models that we use for constructing our portfolio. And today we use classical solvers for those models like Gurobi. And today those classical solvers do give us solutions. It's not that they don't give us solutions. Classically, we do get to the local minimum, but those solutions are always not always the number one, the best solution. In terms of time, it takes a lot of time to get to a normal solution. And if you are aware about the markets and the trading, the markets change every minute, and sometimes by the time you reach a solution, the price has changed and you might have to do the rebalancing again. So things like that happen. So that's why we selected this as the problem, and seeing like if there is a way where we can use quantum algorithms or quantum inspired algorithms or quantum optimization to solve this kind of problem, where we are trying to get to a decent portfolio with optimal solution in a decent amount of time. So that was the whole reasoning behind that. Now, to do that, what did we do in this step? In this step, if you see over here, we basically found out how today the business creates the portfolio. So today, if you look at the process of creating the portfolio, it's around basically 4 steps. First is the inputs. We take basically what are the inputs we require to create that particular portfolio. So that input can include expected returns. It can include the market volatility. It can include the correlations between the asset classes. It can include the risk. It can include the uncertainty and several constraints. And the constraints can be internal or external. So those are the inputs that we typically use when constructing any portfolio at Vanguard or constructing any ETF at Vanguard. And then we basically define the functions. Okay, what do we want to maximize in terms of these inputs? What is our constraint function going to look like? So we create that function, and one of the function in that is maximizing the expected wealth. It's a max function. We do have min functions also, but for this particular use case, we won't be using that. So it's like a maximization function where we want to maximize the expected utility of the wealth. So that is the function that we do. And based on that, the asset allocation happens. And based on the asset allocation, we basically measure what is the probabilistic risk and return expectation based on the allocated assets, what is the expected maximum drawdown, and what is the expected Sharpe ratio. Those are the 2 to 3 things that we measure as an output for different portfolios that we construct. So we go through that process and basically create those portfolios. And at the same time, we also make sure like this kind of portfolios that we create are the ones that are giving us good returns in terms of benchmark indexes that we have created. So it's a pretty complex process. What you see over here is just a simple overview, but as you go into the project, as you look at the data, as you look at the different steps, you'll see in detail like how this particular thing works. Right? So for this particular use case that we are going to show you guys, we are going to use something called as a smaller version of our Vanguard asset allocation model, which is known as one opto model. So what is one opto model? So one opto model is one of the models that Vanguard has created to create ETF funds for bonds. So if you are familiar with what are bonds, so bonds are like an instrument that you can put your money against. But those are fixed income instruments. They are not equity instruments. Like, they are slightly different from equity. They are like called as a fixed income instrument. So the bond funds are also known as fixed income funds. So every year we use this one opto model to create 2 to 3 new fixed income funds. Now, the creation process itself is very comprehensive, but another challenge that we have after creating this fund is, if we have to basically use this fund that we created, to trade on the market, what is the most optimum trading strategy? That is one of the challenge that we have in terms of using this particular fund that is created. So today, what our team has done, right, the fixed income group, they have created a model. That model is called as 1 Octo. And what they do, they use this particular model, and this model has been built on top of Gurobi. So they use this model to trade these bonds for their funds. So to give an example, it's there in the next slide. Let me walk you through that and come back to this. So this is how the process works. Okay. So today, if let's say Vanguard, we are the ETF sponsor, we want to create an ETF for a particular bond. Now, the way this market works is like you don't directly, Vanguard does not directly go to the exchange and basically create the ETFs. They go to authorized participants in this particular case. So what is an authorized participant? So authorized participant, they offer you a set of bonds in terms of in basically exchange of ETF. So think of this like a scenario. I'll give a very what you call a simple scenario. Let's say you want to buy orange juice. So there are two ways to buy orange juice. One is you buy oranges and make the orange juice. Second thing is you directly go to a store and buy orange juice. So think of that scenario over here. So in this case, the exchanges are what are the markets that are selling the oranges. Now Vanguard has the option of directly going to the exchanges, getting those oranges, determining which oranges are good, which oranges are bad, and creating the orange juice and sending basically giving it to the stores like let's say Costco or stores like others. But another option is, let's say Vanguard does not want to fall in the process of making that orange juice. They simply say, okay, we will pay you. We will basically pay a middle party saying, you create the orange juice. What we will do is simply purchase it as in bulk from you and sell it in the store. You handle the process of determining what oranges to use. You basically determine the process of which oranges are good, which oranges are bad, and you simply give us that. And in turn, we'll give you basically the pricing for that wholesale orange juices. So those are the authorized participants. What they do, they go to the market, they basically find out which are the funds that they want to give to Vanguard, and they create that orange juice and then give it back to, or give those orange juice boxes to Vanguard, and Vanguard sells it in the market. That is the process that is explained over here. But one of the challenge over here in this process is like there are, let's say, 10 manufacturer of those orange juices. How do we determine like which is the manufacturer we should go to get that orange juice? Should we go to manufacturer one? Should we go to manufacturer two? Let's say if we go to manufacturer one to get orange juices, how many should we buy from them? Should we buy 20 orange juice crates? Should we buy 30? How much from manufacturing two? So if you look at this, also becomes like a transport logistics optimization problem. It's very similar to that. So here what we have to determine is, let's say my authorized participant is JP Morgan, or my authorized participant is Goldman Sachs. How much of ETF shares should I give to my JP Morgan, and how many bonds should I buy from them, the underlying securities, to create my ETF? Should I buy 10 bonds that they are offering? Should I buy 15 bonds that they are offering? Should I buy 20 bonds that they are offering? And same thing, if I basically, let's say my ETF that I'm trying to create consists of 100 bonds, just for example, where should those 100 bonds come from? So let's say if I go to JP Morgan and tell them, oh, I'll take 10 bonds from you. If I go to Goldman Sachs and I say I want to take 20 bonds from you. If I go to State Street and say I want 30 bonds from you. How do I determine which 10, which 20, which 30? That's a typical difficult problem to solve in short time. Because if, let's say, the authorized participant, they offer you a basket, they come with a basket, they're saying, oh, this is my crate, this I've got 100 orange juices. You pick which 10 you want. Not my problem. I've created, you asked me to create that, I've created it. Now you determine which one you want to pick. So how do you determine which one to pick and from whom to pick? That is the optimization problem that we are trying to solve. Like when we go to authorized participant, how do I know which 10 bonds to pick, which 20 bonds to pick, which 30 bonds to pick? And once we determine that, we create our own basket and we create our ETF shares and then hand it back to those authorized participants. So once we get our 100 bonds, we create our ETF and then give it to authorized participants who go and sell it in the market. Right? They don't know what we use. It is up to us how we use it. So this problem that you see on the screen, although it sounds simple, it's like selecting from a basket. But how do you make sure you are selecting the thing from that basket? That's the challenge. And that is one part of the challenge. Second is once you select that, how do you make sure it's actively tracking the index? So index market is slightly different from an equity market, wherein you have to track the index of the overall market. Like let's say if the overall bond market is going down, your ETF also needs to go down. If your overall bond market is going up, your ETF also needs to go up. So that is second constraint that you are introducing, which is like the index tracking. Like every time the overall bond index changes in the market, how do I make sure I'm tracking it correctly and basically following it? So that is the basically the second constraint that comes into it. So that the whole process, the creation and redemption of ETF share, that is basically one of the largest problems in terms of portfolio optimization that we solve today using Gurobi. And as I said in the beginning, we use classical solvers to do all this thing. And what we are exploring now is how can we use quantum algorithms to do this kind of work. Instead of running this problem on Gurobi, are there variational algorithms that we can use? Are there hybrid algorithms that we can use? Are there another kind of algorithms which are quantum inspired that we can use? So we started our experimentation with VQE, right, the variational algorithms, and we were getting some decent amount of results. But as we know, quantum computers, they have their own challenges in terms of errors and in terms of scalability with the qubit count, the logical qubits. So we could only run this problem roughly around 130 to 200 bonds. In real world, the ETF share that you see consists of more than 1,000 bonds. Like one of the ETFs that we have, it consists of 1,800 bonds. And that those 1,800 bonds come out of the market of around 40,000 bonds. So if you can imagine, right, selecting 1,800 out of 40,000, and that too from different participants, it's not that easy. It's a pretty complex scenario where you have to find out, okay, what is the best ratio that you are going to get in terms of the Sharpe ratio. So that's the problem that we are going to give you as a challenge to solve. All the data will be provided for this challenge. You will also see how Gurobi does the process, what is the output from Gurobi. If you're not aware about Gurobi, it's like if you have worked on linear programming, it sort of does some sort of linear programming, but it's much more than that. But in terms of simplicity, just think of linear programming. You create multiple equations, you give that equation as input to Gurobi, and Gurobi solves each of them and gives you the optimum answer. So that's the problem that you will see. And basically over here, we have defined the limitations of Gurobi. So as I said, a typical portfolio basically consists from 100 to 10,000 bonds. And higher the number of bonds, it's very, very difficult to run this kind of a problem in Gurobi within 5 to 10 minutes. Today, the problem, the largest ETF that we created, which is around more than 1,500 bonds, on Gurobi typically takes 8 hours. And as I said, by the time that 8 hours, the bond price can change because it's a market. The trading happens every minute. If let's say I started my optimization problem when the bond price was $10, and by the time my optimization problem ended, the bond price is $12, I cannot use the output from that. I have to rerun this with the new price, assuming this new price won't change. So a lot of these processes are run overnight, and they are not run during when the markets are open, just to handle the price stability. But where we are going with this is we want to run this in real time, like bound it between 5 to 10 minutes or 15 minutes. Today, you can bound it on Gurobi, saying, oh, Gurobi, don't take 8 hours, run it in 10 minutes. But then within 10 minutes, the kind of solution that you get may not be the one that you will get after 8 hours. So if you know the concept of local minimum, global minimum, this will give you a solution that is closer to local minimum, not even local minimum. After 8 hours, it might reach local minimum too. But reaching global minimum in Gurobi, it can take days also. So the idea is like, how do we get to the most optimal solution within a bounded time? And let's say even if we take more time, let's say even if we take 1 hour or 2 hours to solve this compared to the 8 hours, and we are still getting a better solution compared to what 8 hours is giving, that's still a win. So the idea here is like the model that we have created, how do we take that model, either make it better or faster? Those are the two challenges that we have. Like our value is measured in terms of both, like either give us a better model or give us a faster model. So we will leave it up to the participants to determine what they want to work on, either improving the speed of getting to the optimum answer or getting to a better answer at the same time. And this is the mathematical formulation. I won't go into this. This we will share once we start the project onboarding. But just to give you an overview, the kind of parameters and the kind of mathematical functions that you'll see. So this, as I said, it's a maximization problem. All these are the input parameters: the market price of the bond, the minimum trade volume, the maximum trade volume. How much bonds do we want in that basket? Like remember the basket from that authorized participant, and how much can I increment? Like sometimes authorized participants say, oh, you cannot basically take 12 bonds from me. Either you take 10 or you take 20 or you take 30. So it's like increments of 10. Some authorized participants will tell you, oh, you take 10, 15, 20. So that increment is basically determined by the authorized participants of how many you can increment in the basket. So in the basket, if I want, let's say 20 or 30 bonds, I cannot say 20 to 23. I either take 20 or I take 30. So that's the thing. And how much minimum capacity do I have to trade? The maximum capacity to trade. And then we have some global parameters. And then these are the constraints, like how many maximum bonds can be in a basket, what is the cash flow that we need for the Sharpe ratio, and then the characteristics of the risk that we have defined, and the constraints on the binary variable. And this is the overall objective function. The objective function is a min function. It's basically the reverse of the max, the constraints that you see. So it's like a minimization function of minimizing the risk or the covariances between the bonds so that we get to the local or the global minimum. So we'll go into details of this as we start the project. My team that I basically introduced in the beginning, they will help you support all these different things. So I think we are at the top of the time. I had to rush through this quickly. But as I said, don't worry, we will be sharing this material as we start the project onboarding and everything. And as we go through this, you will learn more and more about what this project is about and how this project basically will help us gain value and how you can help us gain that value. So we have 3 minutes left. I just wanted to see if there are any questions before we wrap up this topic.
Sure. Yeah. Thanks a lot, Bimal. As far as time is concerned, if you do have more slides to cover, you can take more time. Our next speaker might be delayed. So yeah, we can go through questions as well. It's up to you.
Okay, got all. So one thing I wanted to basically cover is what we are going to do for this program is we are not going to give you a complex equation like this. For this program, we are simplifying it. So if you see over here, for the proposed problem formulation that we are going to do for this portfolio index tracking of bonds, we are simplifying it. So we are only going to consider binary variables, whether the bond is included or not included. We are not going to have that kind of minimum constraints, saying this basically just include 5 bonds, 10 bonds. So we are going to simplify those constraints. There are no integer variables, but we are also removing the constants, the beta constants that we use for Sharpe ratio. So that is also not needed. And relatively small size. So the idea is we know the limitations of quantum computers. So we are not going to give you 1600 bonds and tell you to optimize that. We are going to restrict this problem to something under 300 bonds. So optimizing 300 bonds, and within those 300 bonds, determine which bonds are we going to select in the basket, which we are not. So the output is going to be simple, right? Out of the 300 bonds, what we want is like equation, a simple equation saying 101010. It's like a binary equation which tells us which bond should we include in the portfolio, which bond we should not include in the portfolio, based on the constraints that we start with, which are the binary variables and the simplified constraints. So this is the simplified problem formulation over here. Like if you look over here, decision variable, we have basically changed that into this. This will be your decision variable. The constraints are going to be there, but you can ignore some of them which are not binary, and objective function stays the same. So the thing is, like between constraints, you can use the constraints that are only binary constraints. And over here, the decision variables, basically it's simplified now, where we just say whether to include a bond or not using this particular function. So that is the idea today. So we as I said, we tried this on our own, and we basically used variational quantum algorithm, as I said, to do this. This is something we are still working on. So I don't think we are going to share this with you guys because we want to see what you guys are going to come up with. So that's the whole idea. So we will share the slides, we'll share the problem, we'll be sharing the data. What my team is doing is they are setting up a GitHub repo where all this will be shared. You'll get a link to that repo. The idea is you basically need to copy or clone that repo and work on this problem as a team. You can form your teams. I think Vardaan and team will give you the logistics around that. But the idea is like you work as a team and then present as a team. And from presentation perspective, what we are looking for is a solution in terms of do a show and tell. Like you basically took the data, you basically created a solution and do a show and tell, saying this is how we came up with the answer and this is what it looks like. We are not necessarily looking for a deck or a presentation here. The idea is we want to make this more flexible and more what you call intuitive rather than restricting it to a deck. So in presentation, if you can do a show and tell and simply show us what is the solution that you came up with, what the output looks like, and what does it basically make it work. So you can use your own algorithms, you can use your own hardware, you can use your own simulators, whatever you prefer. So that we leave it up to you. But the idea during the project phase is like be how much ever innovative you can be with this particular problem and come up with a way where you think, okay, this is the best way to optimize this. All right. Yeah, so that's it from my side. So back to you, Katie, Vardaan.
Wonderful. Yeah, thanks a lot, Bimal. This is amazing. I love this. And I feel that the participants are loving this too. We have already seen a lot of responses that, hey, this something of interest to us, we want to participate and then form teams. So yeah, we are already seeing a lot of excitement from the participants. This is great. One quick point you mentioned to the end of your talk that this would be platform agnostic. I just wanted to reiterate that point. All the participants are free to choose any hardware, any simulator, any platform they are most comfortable with. So they don't need to restrict themselves to, let's say, Qiskit or IBM systems, or they can use anything. And if any of the participants or teams do receive significant results in, like, say, in the middle of the project timeline, we can also offer some hardware support from our side. So definitely, we'll share more information about all that goes by July 1st. So yeah, let the questions come in the live chat channel on Discord. I'll just monitor that, and maybe we can take a couple of questions.
So we've got one from Ron in Chicago, who asks what sort of data for each bond or instrument needs to be considered as constraints.
So that is a set, the data that we'll give you. There are certain constraints that you will see are the binary constraints, like what is the maximum amount that the bond can basically trade at, what is the minimum amount it can trade at, what is the variance. So those are the constraints. All are mathematical constraints, but there are even binary constraints. So it's up to you whether you want to use the mathematical constraints also along with the binary constraints. But both kind of constraints are available. What we did, we limited it to binary constraints. We did not use the mathematical constraints now because it was very difficult to model them on a quantum computer. But if you guys think you can do that, that will be awesome.
Thank you.
Okay, I have another one. This might be very relevant to your past experience as well, though. So the question is, we have had talks in the past which mentioned hybrid approaches for quantum applications. You coming from a vast experience of AI and machine learning, do you feel there is some sort of convergence between machine learning and quantum computing, or are they two completely separate? And would you recommend hybrid approaches for the participants to explore here?
Yeah, so machine learning and quantum computing. You might have heard the term QML, the quantum machine learning, which is basically gaining traction. Now, there is no proven advantage of using QML because one thing is it does not basically give you the results that its classical counterpart can give. Second thing is it does not give you better results than classical counterpart. So the classical counterpart still gives you better results in terms of machine learning. So machine learning algorithms are still being worked upon. But what we are also seeing is quantum inspired algorithms that are gaining a lot of traction, like tensor networks. That is another area that we are actively exploring in terms of solving this kind of problem. And the hybrid approach that we used over here, it's like a hybrid approach of variational algorithms along with the sampling. So you can use variational algorithms along with sampling, and you can use that approach too to basically simulate this kind of a problem. It depends on what kind of a variation approach you can use. So QAOA, that is one of the variational algorithm that also uses hybrid approaches. What we used is VQE. We use eigensolvers and use sampling-based methodology on top of eigensolvers to achieve a scale of around. We started with 16 bonds, then we scaled it to 110, and now our team is now scaling beyond 200 now. So that's why we have limited it to 300 bonds. So it all depends like which one you want to use. But machine learning is one area that is definitely evolving. And quantum machine learning is something we are actively investigating for anomaly detection too within fraud space to see if there are some algorithms that can fit in that. We are actively looking at penny lane now and exploring a lot of algorithms to penny lane and when it comes to quantum machine learning. But that's a very what you call research area. It's not like some area where we know that there will be advantage in future. It's like an area where we are unsure, like what will come in the future. We would require some very different algorithm. What is happening in that space now, at least in my opinion, is people are just copying the classical algorithms and trying to make them quantum. What is actually needed over there is some different algorithms altogether, like quantum algorithms, which are not available classically. That is what is needed over there. So if that happens, then definitely there will be growth in that area.
So yeah, that's a very fair point. And who knows, we might end up collaborating with you guys on a research project around quantum machine learning for all the participants.
Yeah.
So yeah. Another question I have is, how many qubits would you be expecting to run portfolio optimization on, let's say, an asset? And how does that compare with Monte Carlo or traditional optimization approaches?
So we were able to run this on the IBM. The latest one that we have from IBM is 140 qubits or something like that. We were able to run our 110 bond problem on that by mapping each and every bond to a qubit and then utilizing certain qubits for constraints too. So the IBM 140 qubit computer that is available today, we were able to run it on that. But you may not be able to run it on the free time. So IBM offers 10 minutes of free time every month. That won't be sufficient to run this. When we ran it, it took at least an hour to run this kind of a problem on that particular computer. But IBM is a partner, so we get access to their machines. So if you're thinking in that angle, it won't work on the free version. But at the same time, we are also looking at D-Wave, the hybrid solvers that D-Wave offers, and we are trying to run it on them too. And just recently, our team also was able to scale this problem using the decomposition methodology to run it for more than 200 bonds on a similar size computer. So it depends on how you are tackling that problem. Like what kind of pre-engineering are you doing to that problem so that you can basically run it on the current available hardware. So a lot of pre-processing, post-processing needs to be done in this kind of work. Like how good that pre-processing, post-processing also determines that.
We've got a question. Is quantum annealing user here? Is quantum annealing better here? I believe might be the question.
We haven't tested that. That's a good question. We haven't tested quantum annealing. We haven't gone down that route. Now all we did is we started with superconducting qubits. And superconducting qubits use gate-based approach. So we haven't yet delved into annealing algorithms for this kind of thing. But if you think you can achieve something with using annealing algorithms, we are more than happy. That's why I said it's hardware agnostic. It's up to you what you want to use. But we haven't tested that yet.
Thank you.
Another question could be, how are the participants expected to benchmark this? Are there certain criteria from Vanguard where the participants kind of benchmark their solutions against?
We'll be providing that. As I said earlier in the call, we created our own benchmarks and we would like to compare against them. Yes.
Wonderful. Another question is on, something you mentioned early on in your talk, that there is a trade-off between speed and accuracy for the model. If someone was to make that trade-off, what would your preference be? Do you prefer time? Because you did mention that the rates of these areas change very fast, and we need to have a quicker model, but at the same time, you also don't want a funny solution coming out of your models. So what are your thoughts over there?
So given the choice between speed and quality, our business prefers quality because let's say even if you get the solution later, but if you got a quality solution, you know that solution that we got will work. So those kind of solutions, we run them after the market closes. So no fluctuations happen. So typically after 4 o'clock, we basically start running all the simulations and try to see what is the best solution. So when the market opens, we can use that solution to start optimizing our portfolio and start creating that ETF. So we don't have to wait. So because we do have that flexibility where unless and until like, okay, it's like mission critical or now only we have to create the ETF. Let's say at 12 p.m. we got a request saying or the authorized participant wants to dispose it off. You want to do it now, then we have to run it real time. Otherwise, this is something we can wait if we get a better solution. So the trade-off, yes, like quality will be the winner there.
Fantastic. We have a few more people typing in, so let's just give them a couple of minutes.
Sure.
Yeah, should we take one or two more questions? We probably have time for one or two more if that works with you, Bimal.
Sure.
So we have one here, which is, have you tested D-Wave's new nonlinear solvers or fast annealers?
No, that is something that is in our roadmap towards the next quarter. Good question. Yeah, we basically just had a discussion with D-Wave last week on this. So that's in our roadmap.
Thank you. Who's going to get the final question? We've got someone typing.
Okay, maybe one final question, and this could be more generic one to all the participants over here. We have a large cohort coming from PhD and postdoc students as well. Bimal, I know that you are looking into expanding your team on the quantum computing side as well. So if someone wants to start learning and maybe scaling up into specific niche topics for quantum computing in the domain of finance, are there any suggestions from your side?
Sorry, what was the last part?
What are the different suggestions you could share with students who want to get into quantum computing for finance, like potentially work with Vanguard? Are there any specific skills that you look for in candidates?
So we have started to build our team here. So a couple of skill sets that we are looking is one is the domain knowledge. See, when it comes to finance, it's slightly different from chemistry and material physics. So like it's a lot about numbers, and it's a lot about a lot of problems where quantum can be applied. Falls in the domain of economics, it falls in the domain of risk, and it falls in the domain of optimization. Right? Those are the three primary areas where this thing falls into. So what we are looking for is not just having knowledge about quantum physics and quantum computing, the technical knowledge. We need someone who also understands the domain. How can we apply this kind of a problem to this particular domain? Because quantum computing has a lot of advantage in material physics, in chemistry, we know that, but in finance it's questionable. Like today when we talk to a leadership, we get a lot of questions like, are you sure this is going to work? We are putting money towards this, like, are we going to get any returns on this? So it's a tricky question to answer. So now a lot of research is going in this space, and research is successful if you understand what the domain is for which you are researching. So that is definitely one skill set. So today, last couple of months back, I was at UPenn, the University of Pennsylvania. They have introduced a program which is like applications of quantum in financial and econometrics. That was a very good program, and there were a lot of students who basically presented what they are doing in that space. So that is one of the program you should look at. I'm not saying you need to attend that, but that program has good what you call layout, a structure of how quantum computing can be used in finance. And NC State also has one. Since I am in Charlotte, I know I work with NC State too, which is North Carolina State University. They have a program too, and UNC has one too now. So a lot of universities are thinking in that space, but UPenn one is really good, right? They have been running it for a couple of years, and their student base is quite good too.
Wonderful. We have a lot of feedback coming in from you, Bimal. So we have participants saying that, yeah, you are one of the most amazing speakers with answers. So I am really happy that they are loving your answers there.
Thank you. And I'll share our link. The papers that we publish, there is one paper that Vanguard published last year. Me and my team published it. Like, how are we thinking about quantum computing, and like what are we going to do in that domain? Like, we have created readiness levels, and today, like, we are at readiness level 2. Our goal is, with this program, we want to move from readiness level 2 to readiness level 3 or 4. So I would say, like, if you're going to participate in this project, go through that paper. It's pretty good. I'll share the link, and that will give you an overview of how our quantum team is set up and what we are doing in that space, and how finance is, industry is evolving in that space.
Thank you so much.
Yeah, thanks for inviting me. I'm really looking forward to this work, and hopefully we get more active participation from the participants. So all the best, everyone.